All right, we're going to do an example here where we apply the normal distribution or normal curve to find the probability of a random selected member of the population falling within a certain interval. All right, that was a big mouthful. So let's just look at this interesting sort of situation here. What we have is that it's a question of how long it takes for an egg to hatch. So you can imagine if there's a farm and there's chickens and eggs, there's a question of, well, how long does it take for an egg to hatch? And apparently, if it's in the average incubation time of a fertilized chicken egg kept at a certain temperature here, 100.5 degrees Fahrenheit, in a still air incubator is 21 days. So it takes 21 days on average for that chicken egg to hatch. Now, just given the average isn't really enough. A lot of people say they want to know the range. Okay, is it all the chickens in 21 days they all hatch, or is there what type of range? Is it between 15 and 30 days or something like that? Well, we're going to assume it's normally distributed and that it has a standard deviation of 1 day. So what does that standard deviation of 1 day means? If you look at, well, here I'm going to do it right here. That's the first problem. I am going to draw a picture to describe what's going on here. If I have a normal curve here, here's 21. The standard deviation is 1, so I can easily add 21 plus 1 and get 22. 21 subtract 1 and get 20. So remember that if I have just standard units, which are standard deviations, then between -1 and 1, I have 68%. Why am I doing that? I mean, where's the 68% come in this problem? It is just a way for me to keep in mind what it means to be between 21 days and 22 days. So 68% is 2/3 of the population around. 66.7 is 2/3 of the population. So about 2/3 of the eggs are going to hatch between 21 and 22. Some will be less than 20 days. Some will be more than 22 days, which you could use this to calculate, sort of easily. But okay, so here's our picture. It's what we'll see. I mean, you can sort of see right now that it's unlikely that an egg is going to hatch in, say, 15 days, or unlikely it's going to be within 30 days, because here's one picture of the standard units, and we've talked about the empirical rule. If I look at 2 standard units, that's 95% of the population. So almost all the eggs. Well, no, there's still 5% left. But a lot of the eggs, 95%, are going to be within 2 standard deviations. So that's standard units. So that would take us, since it's easy, we're just adding 1 each time. That would take us up to 23. So, we could see between 19 and 23 is 95% of the population. Okay, here we're not just talking about what proportion of the population. We're going to turn this around and look at this as probability. What's the probability the random selected fertilized egg hatches in less than 20 days? So we're going to let X be the incubation time. I don't usually write that down. I just write down X, because we're just using that all the time. And we're going to write probability X is less than or equal to 20. So you could, and I guess I will, draw a picture yet again, one more time, and color that in. Now for this guy, since I know that that's 1 standard deviation below the mean, I can use the empirical rule. Outside the 68% is 32%, and half 32% is 16%. So too fast, but okay, so we're going to use on the TI-83, we're going to use second distribution 2, which is normal CDF. Okay, so I'm going to write this as normal CDF. I'm going to pick the left endpoint, which is just the largest negative number I can put in the calculator, negative E99, and then it's going to come up to 20. And then I'm going to put the mean, which is 21, and the standard deviation is 1. So this is the mean, the standard deviation. Put that in there. I predict it's going to be 1/2 of taking 100 from 68 from 100. So that's 100 minus 68 is 32. Half of that's 16. It's going to be about 16%. Well, I hope I get that right, but I think I will. So take a little bit of time to use the calculator here. What was I doing? 20, 21, 1. Close it up. Yay, got it. That's as predicted. That's 0.15865. Goes on forever, but that's about 16%. So only 16% of the eggs will hatch in less than 20 days. Then we're looking at the probability over 22 days. Again, I can use the empirical rule because that's within -2 and 2 standard deviations. Okay, so 22 is, oh no, I said it wrong. 22 is just 1 standard deviation. So I can use 1 standard deviation over, 22 minus 21 is 1. So 1 standard deviation over is well, it's going to be the same answer. See, so I have 21, here's 20, 22. I'm doing, by symmetry, it's the same thing. I'll just write this down so someone asked, but it's going to be the same thing. I'm going to go 22, E99, 21, 1. It's going to be, it'll be the same percentage, the same probability because of symmetry. So this is 1 standard deviation above. I mean, you can just figure this out. Z is x minus mu over sigma. That's our formula. So Z is equal to 22 minus 21 over 1, where that's 1. While here, Z was -1. So anyway, you're going to get by symmetry the same thing. So a 15865, etc. So that's approximately 16%. It's not that interesting of a problem. I should have done something different. Would it be unusual for an egg to hatch less than 18 eggs? So what's the probability x less than or equal to 18? And is that something that's really surprising? And I'm going to say yes, because here's 21. 20 is 1 standard deviation away. 19 is 2. 3 standard deviations away is 18. And I can, because of these problems are sort of, these numbers are easy to work with, I can use the empirical rule, which says that if I have between -3 and 3 standard units, that's 99.7%. Okay, sorry. So 99.7% is between -3 and 3. And see, I don't have to calculate this, so it's, you know, being long-winded and everything, but I think you can do this in your head. You have 18 minus 21 over 1, that's -3. So that's 99% here. That's not really what my question is. My question is, what's less than that guy here? This is going to be 100% minus 99.7%. The whole thing divided by 2. So that guy is going to be, you know, it's small. So it's going to be 0.3% divided by 2. So that's, you know, going to be 0.15%. All right. But by the time we're doing that, you might think, well, why don't I just use the calculator? So why burden ourselves with all those numbers? Well, it could be fun. That's why. And also, it could give us a better understanding of what's going on. So we're just going to go ahead and do that. Even though I think I'm claiming I know the answer. So that will be sort of stressful if I didn't get the right answer. My prediction's wrong. If that is true, then I don't know, I'll be happy with that. Okay, the calculator is saying, did I do this right? The calculator's, oh no, I pushed the wrong numbers in wrong. Okay, sorry. Okay, oh, gosh darn it. They're saying 0. It can't be that small. I just can't imagine that it's that small. Well, I'm getting 0, but it's about 0.15%. I just don't think. It surprises me that the calculator is not going to give us a better number in there. But anyway, it's going to be around. It's going to be close to 0. The probability is never going to be 0 anyway. So apparently it's close to 0. Okay, so it is very unlikely. That's not equal to 0, it's squiggle 0. That's the answer. So if you're a chicken farmer, if you're raising chickens, you can be rest assured that your chickens will not, your eggs will not hatch in less than 18 days. Oh, okay. I don't know. I don't know what I did. I pressed the wrong numbers. So it's not almost 0. The calculator gives 0.001349, and that is approximately 0.0014, which is approximately 0.14%, and that's what I predicted over here. Okay, so I don't know. That's the thing about calculators. It's so easy to sometimes put a wrong number in there. So I did it twice. So it's a very small amount. Okay, but it's almost 0. It's very unlikely.